So I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis that is being offered by Professor K. Ramesh on the SWAYAM portal. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering and working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan. So today we will be looking at the contents from week 3 of the course, which is to which is to do with the introduction into transmission photoelasticity and some rudiments. So with that, let us go to the first question. When the relative phase retardation between two light vectors is pi by 2 or 3 pi by 2, the resultant traces a dash with its angle azimuth with respect to uh, with respect to the x-axis as which of the following is what is asked. So we know that when there are two perpendicular waves, rather let me draw it like that. Let us say this is one wave and let the other wave be perpendicular like that, and let there be some phase lag between these two. Now the tip of the light vector, this we have resolved it into two components, essentially this being the axis. So the tip of the light vector is the resultant of these two waves at any point in time. So what is the curve that it is tracing is what is asked. So we know that when two mutually perpendicular waves are to be added and the resultant has to be written down, we have a generic expression in the form Ex squared by Ax squared plus Ey squared by Ay squared minus 2 Exey upon Ax Ay cos delta is sine square delta. The derivation for this is given in the lecture, so you can refer to that. So this being the general expression for that curve, for the locus, that the tip locus of all the points that lies on the tip of the light vector when two perpendicular waves are added. Similarly, the azimuth of that light vector, of that light ellipse, can be given as 2ax ay by ax squared minus ay squared cos delta. So with this background, if I were to see what the question is asking, it says that the relative phase retardation between two light vectors is given to be pi by 2 or 3 pi by 2. In such a case, if I were to plug it into this equation, what is it that I get? I get Ex squared by some generic amplitude Ax plus Ey squared by Ay squared minus 2 Ex Ey Ax Ay cos pi by 2 equal to sine square pi by 2. And what do we know from here? So let me just simplify this, duplicate this. So I know that cos pi by 2 is nothing but 0. And then we know what is sine pi by 2? It is 1. So sine square pi by 2 is also 1. So if that is 0, this entire term vanishes because that is what is multiplied, or that is what it is multiplied by. So this expression, we are quite familiar with this. This is the general expression for an ellipse. So when it is pi by 2 or 3 pi by 2, we can see that it traces an ellipse. and the orientation is as the angle with respect to the x. So that can be computed using our azimuth. So let me duplicate, take it here. So let me substitute tan 2 beta. Beta is the angle that the major axis of the ellipse traces with the x. That is our reference. So this happens to be 2ax ay upon ax squared minus ay squared cos pi by 2. So what does this come out to be? 0. So if tan theta is 0, tan 2 beta is 0, that therefore beta is 0. So what does this tell us? That the ellipse actually has its major axis oriented with our x-axis. So as we rotate in such a case, our ellipse is like that. The light ellipse is like that. I'm sorry. It is like that with 1 minute. This actually, I hope you get the idea what I'm trying to say. Yeah. So this will be along the x-axis. The major axis is along the x-axis. You can just consider it that way. Because, yeah. Let me draw it this way. This is much better. Okay, so this is x and the major axis of the light ellipse is parallel to that. So we get when same goes for when uh, Mr. Shivakumar, if could you kindly mute, please? Thank you. When the relative phase retardation between the two light vectors is pi by 2 and 3 pi by 2 or 3 pi by 2, the resultant is an ellipse coinciding with the reference axis. So this we have found out. Now it is just a matter of when will it be a circle? When we will have both the amplitudes same. For example, if we have a light vector and we impinge that on a retarder, which creates retardation of delta, that is pi by 2, and the amplitudes that get split up between the fast and slow axis be equal. In such a case, we will get a circularly polarized light. Okay, so this question says, in optics, the refractive index is defined for what? And it is related to which of the following? The options being, the refractive index is defined for a beam of light and is related to the amplitude of light in the medium. It is defined for a material and the opacity of the material. It is defined for a material and the speed of light in the medium. It is defined for a beam of light and is related to the speed of light in the medium. It definitely is related to the speed of light in the medium, and it is material specific. So it is defined for a material. So for any material is given as c by v in that material. Speed of light in that material. So that is how we define a refractive index. So what essentially happens inside a retarder? Let us say that this is a retarder which has a thickness equal to this. So when light impinges here, it gets split into two waves as we are able to see here. And these two waves acquire a retardation delta, relative retardation delta. That is, one lags behind the other by delta, or the other way to put it out is one is ahead of the other by delta. Delta being some fraction of the wavelength. So this happens. For example, if we have crystal, naturally crystals are birefringent. So when light impinges on that, it gets split into two rays, which travel in mutually perpendicular planes and acquire a phase retardation. So when we see anything through a crystal, we will be seeing two images because of these two refracted rays. Similarly, there are certain class of materials which we call as birefringent. They possess a property called stress-induced birefringence. So normally in their normal unstressed state, they are optically isotropic, meaning there is no special preference to any light wave. As soon as we stress it, each and every point in that model behaves like a crystal, and introduces a retardation between the two refracted. It's first of all the light impinges on that material point, which splits into two waves, two refracted waves, and those two refracted waves acquire a phase lag, phase difference, as they move about in that medium. And from the moment they enter to the moment they exit, it has acquired a phase difference because there are two refracted rays. So each refracted rays, as we saw here, is related to a specific velocity. C being constant, there is a specific velocity. So in a birefringent material, there will be two velocities. So naturally, when there are two different velocities, there will be a phase delay when it reaches the outer phase of the model. So this retardation is proportional in some sense to the stress induced at that point. So this is why we call it stress induced birefringence. And this property is what is exploited for the analysis, stress analysis in photoelasticity. So with that said, if we look here, we are able to see that they have labeled one axis called axis 1. So this is axis 1, and we have another axis 2 here, and these two are mutually perpendicular. So as soon as light impinges, we are able to see, I'll just draw one of the curves in blue. It goes like that, and then it is here at this instant. The other one, let me draw it in red. The other one goes like that, and it has reached this position where we are able to see that there is a phase difference of delta. So we can clearly see that the light wave that has passed parallel to axis 1 is leading the one that has passed through axis 2, meaning the red is leading the blue wave by delta. So the question asks, a zoomed in view of a crystal plate is shown in the figure. As a polarized light enters the plate and gets converted into two polarized beams of light with a phase difference as shown. Okay. Axis 1 and axis 2 are marked in the figure. Identify which is the fast and which is the slow axis. Type enter F for fast and S for slow. So we can clearly see that red leads the blue one. So red is fast and axis 2 is slow. So I hope that is clear. Anyway, so the next question asks, light travels faster in ice than in a calcite crystal. Is it true, false, or is it difficult to predict? Well, for nearly all known materials, there have been characterizations where scientists have determined its refractive indices. So this is just a question of referring back to the refractive index that is shown in the lecture. So I just looked it up. That is why I am saying this. But nonetheless, you have the general table given. Such questions are posed with the idea that when we look up some things and try to get the answer, there is better retention. So N for ice is actually less than N for calcite. This is around 1.3 or 1.4 or something. This is around 1.6 or so. So we know that this is the case. And we know from here that n of a material is refractive index of a material is c by the velocity. So n neta, I mean, not n. Neta is inversely proportional to the speed in that material. If that is the case, then we can clearly conclude from here that velocity in ice is greater than velocity of light in a calcite crystal. So, which is what is actually given. So, this is true. So, I hope that it is clear. If there are any questions, please go ahead and ask. In the meantime, I'll move forward. And I think someone had posted in the forum that the questions that attendees are asking is not audible. The thing is, there is a technical difficulty because when I record that system audio also, there is a lag that takes place. So while rendering the video, it creates a problem. So to circumvent that, what I would rather do is whenever somebody poses a question, I myself will repeat that question for clarity so that people who are watching this later can at least grasp as to what was asked, and then I will subsequently answer that. So I hope you can bear with that. Yeah, thank you. Okay. So let us move to the next question. This is an interesting one. In the figures, P and A indicate polarizer and analyzer respectively, and the relative orientation of both the elements are shown, indicated by Roman numerals. These, so there are four arrangements is what is given. Enter the appropriate output light intensity indicated by letters A, B, C, and D over here. So before that, I'll just give a quick brief about what is it that we are talking about here. So in photoelasticity, we saw that it works on the principle of stress induced birefringence. So let us say we have a model like that. Let us say we have a model like that, and it is subjected to some traction, some boundary condition like that. So it is stressed, and let us say that it has this property of stress induced birefringence. So this will have some thickness. This will have some thickness like this. Excuse me. So let us consider a material point over here, and let me zoom it and see what happens. So basically, I will impinge light from behind the model while it is stressed, and I am trying to check the output light. So in order for me to understand what is the difference in the light characteristic that is brought about by the mechanics of the problem, it is necessary that I have control over the input light. So I have input light over here. This is light input. And then from here, we will get one output light after the model. So our interest is to study this, study the changes brought about by light in the light because of the mechanics, because of the stress that is induced. So it is very necessary that I have control over this input light. So there are certain combinations that I can have. For example, we have something called a polarizer. Basically, if we see the normal light source, it does not have any preferred direction. So the light vectors, if you see, it is randomly split with different amplitudes in all directions. So there is no specific control. So that light is called unpolarized. So there are certain materials, something called dichroism. So basically, these are having a preferred direction. For example, this we name it as a polarizer. So what it does, even if I impinge light that is unpolarized over this arrow indicates that it will allow light only parallel to that direction, and it will absorb all other light vectors. So even here, if there are light vectors that are in random directions with random magnitudes, out of this, I will have only light passing like that, only parallel to that polarizing axis, and all other light rays will get absorbed. So this is what a polarizer does. Similarly, we have something called a quarter wave plate, or rather, we have any optical element brings about a retardation that sets in, and this can be controlled. This we will see in more detail in the next session when we deal more with crystal optics. But as of now, you can take it that when we pass light through that medium, we can actually have control over what is the retardation that is brought about, and what is the orientation, how it gets split up. Once we have control over this, we have control over the light ellipse, which implies that the light that we are going to impinge on the model, we know all the characteristics of that light. Once we know all the characteristics, we can record what the output is, and based on our knowledge of the initial light that input light that was impinged on it, we can deduce what is the difference that was brought about because of the stressed model, which is our purpose of analysis, which is the main motive in our stress analysis. So this is just a brief theory. So now we can clearly see. So from here, let us say, for example, let us say that we have a polarizing sheet like this, and polarizing sheet will be shown with always with an arrow. This arrow implies the axis of the polarization. So whenever we see light through this, it will allow light only parallel to this direction, and it will absorb all other lights. Similarly, if I were to have a polarizer like this, let us say at 45 degrees, so it will allow light only at 45 degrees. So this is, we can rotate as we want it, and it will allow light like that. So in such a case, let us say that I have a polarizer like this. I take another piece of this polarizing sheet, and let us say I keep it like this. Now what would happen if I were to see light? Let me call this 1, let me call this 2. Now let us say that there is a light source. Let us say there is a light source like that. And what I do, I take this polarizing sheet and I view the light source through this polarizing sheet. Let me put that polarizing sheet here. Let me put it here. For the sake of clarity, I don't want to put it over this, but you get the idea that light is coming out of the plane of the paper and we are trying to view it like this. So once we view through this, what is it that we will see? We will see light that is essentially parallel only to this direction, and all other light vectors will get absorbed. So now after this step, just a moment. Yeah. So once I have placed this, I have light that is vertical. Now what I do, I take this sheet and I try to view the light. Whatever was coming out of the first polarizer, I try to view it with this. Or let us say that I took it like that and I put it here. What is it that I expect to see? I will see only one component of that vertical light vector. If I were to place it like this, if I were to place a second polarizer exactly parallel to that, whatever light got transmitted by the first polarizer will also get transmitted through the second polarizer, and I will see it in full intensity. Whereas let us say that I rotate it like this. Just a moment. Let us say that I rotated it by 45 degrees. Now what do I expect to see? I will see only one component of it, or one component of that light vector, which will get resolved into cos 45, sin 45. So only cos 45 I will see. Sin 45 will get cut. So in that case, if I were to make it exactly perpendicular to that, what is it that I anticipate to see? There will be no component that will pass through this light, through the second polarizer. In that case, if I view the light source through this, and then if I were to place it like that, I will see absolutely no light. So if I place those two sheets like that, I won't be able to see the light source at all. Now the first polarizer, we term it as the polarizer itself because we are trying to control the unpolarized light. The second, when we take the same polarizer and we rotate it by some angle, and then we try to study the output light, we are essentially trying to analyze the output light. So which is why this we term it as analyzer. Essentially both are polarizing sheets only, but just for the sake of clarity, we name them as polarizer and analyzer. So with that background, if I were to address this question, let us read it again. In the figures, P and A indicate polarizer and analyzer as we discussed. Both are one in the same, but in different orientations, respectively. And the relative orientation between both the elements are shown, indicated by the Roman numerals. Enter the appropriate. So what are we seeing in the arrangement 1? It says that polarizer is kept at 90 degrees, which means this. Let us say that our coordinate system is horizontal invariably. In that case, this is at 90 degrees with that horizontal. No, this is 90 degrees. So the first polarizer is like that, and the analyzer is also at 90. So as we saw, if I take this, I place it like that. So all the light will get passed through that. So which is the brightest here? I can see that D is the brightest of all. Let us first rank this in the decreasing range of brightness. Brightness is a qualitative term. I just mean how much light is coming. So we are just trying to measure that qualitatively. So D is brighter than A, which is brighter than C, which is brighter than B, and we are able to see B is totally dark. So this is the range, this is the decreasing order of brightness. So when both are parallel, I can deduce that what I will see is whatever light was impinging on the first polarizer, I will see it as it is. Just that it'll become a little dim. Why? Because initially I had impinged unpolarized light, and only one of its components survived through the first polarizer. All other got absorbed. So naturally there will be a reduction in the light intensity. I hope that is clear. So this is D. Then I have this has come to somewhere around, if this is 90, then this has to be 45. So this is somewhere around 60, 65 or so. So 90 or 65, what can I expect? Component of that is what will come. So this will be A. This will be A. Similarly, this will be C. And here it is given that one is at 90 and another is at 0 or nearly 0. So that is why we are seeing that all the light nearly is getting cut. So that is why this is B. So I hope this is clear. If there are any questions, please go ahead and ask. Is it clear? Okay, fine. Okay. Now this polarizer and analyzer, and when we put a light source and then we have a polarizer and we have an analyzer. In between, we will try to place this model. So essentially we are impinging light that is polarized, that is in our control, on a model, and we are trying to analyze the output light vector. So that arrangement, that setup apparatus is called a polariscope with a light source and optical elements with the model. And there are different arrangements of polariscope depending on what components, what optical components make for it, which will come in the next session. So we will address it then. Okay. Okay. So it's that same question. Light intensity in orientation 1 is, we have seen it is D. In orientation 2 is A, C, B. So it decreases like that. A, C, and B. Very well. So let us move on to the next question.
Okay, perhaps during the recording of the live session, I was not quite feeling 100%. So I think I didn't do proper justice to solving this question. So I thought I'll address it once again, afresh. So question number 10 says, answer true or false for the following statements. Type true and false in one particular manner. That's fine. So the option reads A. When light passes through a crystalline media, light gets refracted into two unpolarized rays of light. Now let us look at this statement. What this says is light passes through a crystal. Light passes through a crystal, and it says, it qualifies that it is refracted. And then it qualifies those refracted rays as unpolarized. Now, what is to be noted here is that the question itself qualifies the rays to be refracted, in which case we know that the light has impinged on the crystal at an angle that is not zero to the optic axis of the crystal, because when the light is parallel to the optic axis, of the crystal, it passes unaltered, and the crystal doesn't show birefringence in that case. So by the very fact that it has been qualified as refracted implies that it is not parallel to the optic axis, in which case any refracted ray would have to be polarized, which is why this statement is false. Now coming to the second option, crystalline solids are optically isotropic. This is not true. Why? Because crystals have something called an optic axis, and when we talk of an optic axis, if light is parallel to the optic axis, passes unaltered. If it is at an angle, then it shows a birefringent phenomena. And then when it is 90-degree birefringence, I mean both the refracted rays travel in the same direction but with different velocities and so on. But essentially these two very statements tell us that there is some directional dependence, and isotropy implies that it is independent of the direction, which is why this statement, crystalline solids are optically isotropic, is false. It is anisotropic. Well, let us look at the third option. Light passing through a crystalline media gets refracted into two polarized rays of light which are perpendicular to each other. Well, this is true. The planes of polarizations are perpendicular to each other. Light passing through a crystalline media, option D, light passing through a crystalline media gets refracted into two polarized rays of light with the same velocity. Well, we have spoken of refract birefringence, and which implies that there are two refractive indices, and if there are two refractive indices, naturally there have to be two velocities of light in that medium. Hence, it cannot be with the same velocity. So, this is clearly false. So, the option as it stands is the first two being false, the third is true, and the fourth one is also false. I felt that I didn't quite explain this very clearly in the live session. So, I hope I've done some justice to explaining this now. And there were some follow-up queries on this, which I would like to address now. So, question number one was that crystals cannot support unpolarized light. But what if light is parallel to its optic axis? Then yes, it passes unaltered. If light is parallel to the optic axis of the crystal, it passes unaltered. But there is no, as such, there is no contradiction. And as for the second question, how do we identify which is the fast and which is the slow axis? So in one of the questions, it was given that uh, one of the waves, it was in fact demonstrated that one wave in this question, we could clearly see that the red wave, so to speak, is faster, which is why we labeled that as the fast axis. But in general, how do we identify that was one of the questions. Generally, this is done by analyzing the handedness of the light ellipse. Analyzed by studying the handedness, meaning left-handed or right-handed ellipse. Handedness of the exit light ellipse. So this is how that is essentially analyzed. But as such, for our purpose of stress analysis, we don't need to worry too much about this. And anyway, we will see this development in the subsequent weeks. Okay. Figure shows the word beam viewed in different ways. Identify the way in which it is viewed. Enter the appropriate letters opposite to Roman numerals indicating the way in which it is viewed. Enter the letters without comma and spacing. So what we are able to see here, that we have a plain paper where the word beam is written, and we are able to see that it is just one single word that we see. Now we have brought about something in between the word and our eye or this camera, where we are able to see one word here and the other word here. So this is because of birefringence that is set up.
Now we know that for birefringence there are two polarized, mutually perpendicular, polarized lights with different velocities that are traveling towards us because of the crystal. And we know, based on our discussion here, that when there is a polarized light that is coming towards us, and we take this, and let us say there are two polarized lights, and we take this and place it like that. So it will cut out one of the lights, which is what is happening here. So this has actually cut out one light. Now if I were to this, I can see this beam corresponds to the one that is a little written on the top, that is visible on the top. Let me put it this way. One is like that, and the other is, so what is happening is this blue is superimposed with the red. I am just drawing using colors to explain it better. So when it is like this, when I view it through this analyzer placed like this, only this blue is visible, and I know that it is there is a crystal which has uh, two refracted rays, and I'm essentially seeing both of them in two, and these two rays are mutually perpendicular. So in such a case, if this is my analyzer here, sorry, just a minute. So we have taken our analyzer a little. This is one of the analyzers with which we are able to see one of the lights. So what if I were to place it like that? Actually, this comes with an arrow. We should not forget that arrow. So if I were to take it, rotate it like that, perpendicular to this, and place it like this, let us say. So what is it that I'll see? I'll see the other word. I'll see the red one when I see it from here. So I hope that is clear. So with that background, if I were to read the options, A says viewed through a crystalline media and a polarizing element that cuts light from one of the images in the word beam. Where are we seeing this happen? We are seeing this happen in 3. Viewed using natural light without any optical element. That is happening in 1. Viewed through a crystalline media, where we are able to see that there are two. We are able to see that there are two uh, refracted rays that are coming towards us. So this is essentially 2. Viewed through a crystalline media and an analyzer that cuts the light from one of the images of the word beam. Now, what is the difference between option A and option D? It is just that the terminology used, it says this is an analyzer, it says this is a polarizing element. Both are but the same thing, as we saw. One, if we call one the polarizer, we'll call the other the analyzer, because we are trying to analyze the light that is coming out of that polarizer. So with that, we can see that 1 is nothing but B, 2 is C, 3 is A as well as D. Both are correct in this context. So I hope that is clear. I think that is why this without spacing is given. They did not just want us to enter one option. Whatever is correct and relevant to the question, we need to populate them. So I hope this is clear. So, so let us look at this question. Yeah, I think this is what you had asked. Light incident on three crystals represented by 1, 2, and 3 is shown in the figure. The optic axis of the crystal is represented by the black arrow, by the arrow mark, sorry. So this, we have the optic axis. With this information, find which of the following statement is true and enter it without any spacing. Light gets converted into two polarized beams traveling in same direction while passing through crystal 3. Now what happens when we have an optic axis like that and we have light direction that is parallel? When both are parallel, we have unaltered light. When both are at any arbitrary orientation, birefringence takes place and both refracted rays travel in some generic directions. Naturally, because there is birefringence taking place, both won't have the same velocity. So both will travel with some different velocities in different directions. Now, the special case happens when we have light perpendicular to the optic axis. In such a case, we will have birefringence and both refracted rays travel in the same direction. Now they are traveling in the same direction, but they have a phase difference. So we saw in the first question when they are traveling in the same, when two mutually perpendicular light rays are traveling in the same direction, but with a phase difference, what would we get as the output? We will essentially get a generic light ellipse, which can, depending on how we see it and how we adjusted the amplitudes and the retardation, it will get either plane polarized or circularly polarized or remain an ellipse. So light gets converted to two polarized beams traveling in the same direction while passing through crystal 3. This is true. Light is unaltered when passing through crystal 1 because it is parallel. This is true. Light gets polarized when passing through crystal 2. Gets polarized. One process is that light gets split into two and both are polarized. So this is also true. Light gets polarized while passing through crystal 3. This is also true. In fact, light gets polarized in 2 as well as 3. Only thing is it passes in different directions in 2, in some generic direction. And in the case of when the optic axis actually, when the impinging light is perpendicular to the optic axis, it passes in the same direction with that retardation. So I hope that is clear. Okay. So let us look at this question. Parameters used to define the azimuth of a general light ellipse as shown in the figure. So what are the parameters shown? We have beta. Essentially, this is the x-axis. So beta is the azimuth, that is the orientation of the major axis of the ellipse with respect to this x is what is termed as the orientation of the ellipse, which is called the azimuth. Ax and ay are, if this is the major axis, this is the minor axis, we make the ellipse. What are its components in the rectangular coordinate system is what is represented by ax. So when azimuth is 0, I can see that ax will be the point, this point, because when azimuth will be 0, this will be x and this will be y. So this will be ay, this will be ax in that case. I'll just rotate the ellipse that way. And then these quantities are the length of the major axis, major and minor axis, and its ratio is called the eccentricity of the ellipse. Okay, so it is given that ax is 1, ay is 0.5, and the retardation between those two rays is pi by 4, radians. So actually the wavelength of one sine of sine is 2 pi. This is 2 pi. So we are having pi by 4. So it is having a retardation equal to 1/4 of the wavelength. Not 1/4 actually, 1/8. So it will be somewhere around here. I hope I didn't confuse you more. Anyway, what I meant to say is it is one fraction of the wavelength. So what will happen depending on the amount of this delta? Right now we are looking at only one sine wave. If we look at white light, it has multiple wavelengths that are coming. So when the retardation happens, it will pertain to one particular, let us say that there is some retardation taking place. It will manifest itself in the form of different colors of the fringes, because white light is a mixture of multiple wavelengths. So we will look into this more when we go to white light and circular polariscope and white light in the next week. But I just wanted to give a brief about what this delta actually represents in terms of the wavelength. And this can be controlled based on making an optical element thicker or thinner. That also we will see from crystal optics. Why that is useful is, now let us say that there is some sheet that brings about a retardation of pi by 2. So what does this mean? This means that this is bringing about a retardation that is equal to 1/4 of the wavelength or 1/4 of the wavelength. So when we have an optical element that is capable of doing this, we term that as a quarter wave plate or quarter wave optical element, because it can bring about a retardation of quarter wavelength. Similarly, we have that can bring about by pi, that will be half wave plate. So we will see how these are actually made. So that is a function of the impinging light, that is the wavelength of the impinging light, and the optical properties of that material. Based on these two, we can adjust the thickness such that it can precisely bring about a retardation, the desired retardation. And why we are doing all this? So that we have control over the input light that is impinging on the model, that we will study. This is the idea with which we are proceeding. So with these quantities given, it says find the azimuth beta. So beta, let us go back to the first question. We have beta over here, the expression for beta. Let me just copy this and put it here. So if I were to substitute, I have tan 2 beta is equal to 2. What is AX? AX is 1, AY is zero point 0.5. Cos of pi by 4. So what does this come out to be? Tan 2 beta will be 1 square, 0.5 square into 2 is 4 by 3 into cos pi by 4. What does this give me? This gives me 2 root 2 by 3. So 2 beta is 43.313 degrees, or beta is 21.656 degrees. So we have the option 21 points. So what does this mean? Let us say that by some means we have been able to control this, and this is 1, this is just 0.5. So let me draw a square like that, a rectangle like that. Let this be dotted. Now I have an ellipse like that, and this angle is coming out to be 21.56 degrees. Now it will so happen that if, let us say that I was now we can see that in order for me to rotate the light rotate the light vector, I need to adjust these AX AY suitably and the retardation suitably, so that I arrive at this value, which has to be which I have to know before I pinch the light. If rather, as the first question suggested, let us say that I brought about a retardation of pi by 2 instead. In that case, this simplifies to a simple ellipse that has its major axis parallel to the x-axis. So the moment I do that, I have total control over it. I need not go for an additional quantity that I need to account for. So that is one additional benefit we have by having a retardation, desired retardation, that will bring about the effect. Anyway, I hope that is clear. If there are any questions, please do ask.
Yeah, and then there were two more questions that were raised during the session, which which I said that I'll reflect upon and perhaps try to answer in the next session. But let me give an explanation now. And should there be any questions for the viewers, they can bring it up in the next session. So the question was, is the extraordinary and ordinary ray, are these of different wavelengths? It's essentially the question. What we are looking at is a model of some finite thickness, and we are talking about light that is impinging on this model and the retardation that is taking place over the course of this over the course of traversing this thickness. So this light is essentially coming from a light source of one particular wavelength and frequency, which is its characteristic. So that doesn't as such change. Now, when light enters here and it leaves out of the, let me call this the impinging, the front, or rather the back face, and let me call this the front face. Now what happens between these two faces is the retardation is set up by birefringence, and the light essentially has two different velocities. Now the question was that if we say uh, lambda fsc, if we say that this is a constant, then how do we go about interpreting this? Now the thing that is to be understood is this still holds good because our analysis is not inside the medium as such. The light that exits from here, that is what we are trying to analyze. Now it so happens that when the light impinges and this retardation is set up, we are talking about two waves that are interfering with each other to construct the light vector with some retardation. So as soon as the phase lag takes place, what happens is it forms a light ellipse. Because of this, at the output stage, this forms a light ellipse. So this retardation information is embedded into our light ellipse, which is what we are trying to study. In formation of this light ellipse, so this light ellipse equation, which happens to be the function of delta and the amplitudes, it subsumes this information of different wavelengths. And another question that was asked was, is it true that the extraordinary ray is always the faster ray? While it cannot be said that extraordinary ray is always the faster ray, it doesn't cause that much of a problem for us to do our stress analysis because we are essentially looking at the retardation no matter how it is brought about, either it is positive retardation or negative retardation, that we are not that is addressed in the handedness of the light ellipse. So I hope this answers the queries that were raised, and should there be any follow-up questions on this, I welcome the viewers to bring them up in the subsequent session.
Okay, so let us look at this question. Light emerging out of various optical arrangements are shown in the figure. Different types of polarization that the light undergoes are given as follows. A is linearly polarized, B circularly polarized, C elliptically polarized. Enter appropriate letter indicating the state of light corresponding to those different zones. So what do we have here? We basically have a light source here. This is X, this is Y. And then always we won't be having this representation for a polarizer. We know that this implies it will have only vertical, so we will just omit the sheet. We just term this to be a polarizer, which is what has been done here. So we have a polarizer placed like that, and we are able to see. So whatever light, unpolarized light was there, as soon as it passed through that, it became plane polarized in the plane of that polarizer. So after that, we had a retarder, which not only changed the orientation, but it also brought about a difference in the phase, which made which helped in generating a light ellipse.
Now, is something mentioned about Q? Okay. If nothing is mentioned, actually what this Q represents is, Q represents a quarter wave plate. Q represents a quarter wave plate which brings in a retardation equal to, one quarter of the wavelength, which is pi by 2. So this actually, when we say this, it is oriented, this angle is 135. For 90, what we will do is, we have a light vector passing like that. Out of the polarizer, we have a light vector that is like this. Now, if we want circularly polarized light from our light ellipse, we know we have to set AX and AY equal to 0. So, no, sorry, we have to set AX equal to AY. We have to make the amplitude same. So, one way to do this is, I have an optical element whose fast and slow axis are at equal orientations to this. If this happens, then the component of this along this direction and the component of this along this direction is equal. So I have an equal split of light that is passing. In such a case, AX is equal to AY, and we will see that our equation will water down to a circle. Essentially, it will be tracing a circle. So, which is why I said, if this is 90, if this is at 90 degrees, then this will be kept. These two elements will be kept such that angle is equal. So that is why this essentially creates a circularly polarized light, because these two are equal. Once this yellow thing that we see here, that represents the model specimen being tested. And mind you, all this is shown for one material point in the model. That is, we are considering some point in the model which creates a output wave like that. As a whole, if you see the total, that is the total effect of all the response of all the material points, it will show as a fringe pattern. Right now, we are seeing at some one point, particular point we are focusing, and we are trying to see how the light has traversed the path and what is the effect that it has brought about. So after circularly polarized light, this specimen was stressed in some way, which altered the light that passed, and it became some generic ellipse. Now I have impinged a controlled circularly polarized light onto the specimen from the back. And from the mechanics, it has brought about another change to that light, which has led to the formation of an ellipse. Now what I do, I subtract out whatever I had given. Then what am I left with is the mechanics can be attributed to the mechanics of the problem. So that is the approach here. So this brought about a circularly polarized light. What I do, I just reverse that. I just reverse its effect. So whatever I get here again gets converted to a plane polarized light. Now once I have a plane polarized light, as we saw, we will have plane polarized light in one direction. If I were to place an analyzer and view that light, depending on how I orient that analyzer, I will be seeing some light. Now the plane of orientation for this is like that. If I were to hold this polarizer, if I were to keep it like that, I'll see the entire light pass through it. If I were to keep it perpendicular to that, I'll see no light passing through that. But I have kept it at some generic angle. So I'm able to see that this light had an amplitude as big as that. But that amplitude has now reduced. Why? Because only a component of that is getting passed through that analyzer and reaching us. Now, if I were to place it exactly perpendicular, there will be no light here. It will just be empty. The intensity of light that is coming out will be zero. If I were to place it parallel to this, then it will just continue like that. So, in zone 1, I have plane polarized light. In zone 2, I have circularly polarized light. In zone 3, from impinging a circularly polarized light and from the physics of the problem, it got converted to an elliptically polarized light, some generic ellipse. With the quarter wave plate 2, I again bring it back to linearly polarized and I view it through an analyzer, which is again a polarizing element. So that also has to be plane polarized. So zone 1 is plane. Zone 2 is circular. Zone 3 is ellipse. This is after the light passes through the loaded specimen. So this ellipse carries information, stress information. And I want to extract that stress information out. So I deduct whatever I did before, I have to nullify that effect so that I'm left with only the stress information, which is my objective of study. So zone 4 again is plane polarized. And when I view a plane polarized light through another polarizer, it will again be plane polarized with its intensity depending on how I have oriented that polarizer. So this arrangement is actually called a circular polariscope arrangement, where we have two one polarizer and one analyzer we have, and then we have a specimen, and then we put two cross quarter wave plates, quarter wave which bring about a wavelength retardation of this, and they generate a circularly polarized light which impinges on the model. Why do we need to go for this specific circle? Why can't we just impinge the plane polarized light onto the specimen? There are some reasons for that. We will see what is the cause for light extension. Essentially, why we are doing all this, we will, this output light, we will try to obtain that mathematically and then adjust these parameters so that we get only this information out of the mathematical expression of the light, output light that we have. So that we will see when we come to something called Jones calculus, where we will see how we have any optical element, it will bring about a rotation and a retardation onto the light. How that can be controlled and what is a genetic expression. Any material you take, it will bring about a rotation to the light vector and a retardation into the light vector. In that case, how to mathematically conceptualize that and make it so that we are able to arrive at one expression for the output light so that we can study the physics in hand. So these things will be subsequently discussed, but for this, a brief on the crystal optics and how this birefringence works was needed, which was what was addressed in this week. So to that end, I hope I've done some justice. Of course, Mr. Shivakumar has raised some interesting questions. I've taken note of them. I'll go through that and maybe give a well-rounded, try to give a well-rounded answer in the next session, rather than me just blurting out something just to get away with it. I want to address that in its totality. So that I will try to do it in the next session, along with the questions that will be discussed in the next session. So to that end, anyway, I have run out of questions now. Other than this, if there are any questions, I'm happy to take them now. Okay, so I hope this is visible. So this is a virtual polariscope software developed at the Digital Photomechanics Lab, IIT Madras, by Professor K. Ramesh. So basically, why we call this a virtual polariscope is because essentially a polariscope is the apparatus which we use to conduct photoelastic experiments. In that sense, we can virtually do it as if we are sitting and viewing an experiment. We can actually conduct the experiment virtually. So that is why this is called, and we can see here even this carries a lot of information. So we can see there is a light source, there is a polarizer, and we have a quarter wave plate here, and we have some specimen which is loaded. After which we have a quarter wave plate again and then an analyzer. And this is the output we see in the form of fringe patterns. So let me just try to show one problem. For example, let us take a disk under diametral compression. So this, whatever we see on the left side, this is the output that I observe from this end. After the analyzer, whatever I observe is this. So for example, let us say that I took one point over here in that disk. Now I'm able to see that at that point I had the linearly polarized light come, then a quarter wave plate was there which made it circular. Then the light impinged on this point and became an ellipse like that. I nullified it with a quarter wave plate and I put the analyzer like this. So now I'm able to see that the analyzer is transmitting a light that has a big amplitude. That is why we are able to see that this is bright. It is white colored. Now let us say I take another point that is dark, that is almost black. So now we are able to see that here on the right side, we are able to see that the light that is coming out of that is very, very less because it is nearly perpendicular to that light vector. So with this, at any point, I'm able to see the state of polarization. This is the projected light ellipse, meaning if I were to stand here and view the light source, whatever the projected shape, those things we are able to see it here. And we are also in a position to see the fringes in color. Basically, black and white is for monochromatic light. Essentially, it won't be black or white. Whatever wavelength that we supply, that will come here. We can also see it using a white light source, where we are able to see that it is manifesting itself in the form of different colors. So some more on this about how this gets formed, that we will take it up in the next session as we discuss more about Jones calculus and the light vector equations and such. So I hope that is clear. Okay, well, other than that, I don't have anything as such to solve because I've solved the assignment completely. If there are any questions based on what we discussed now or previously, I'm happy to take them. Please let me know if there are any questions.